Hello, students. Look up the next problem. The binding energy per nucleon. The binding energy per nucleon means what? Specific binding energy. Binding energy per nucleon is specific binding energy. So what is specific binding energy of deuterium? Deuterium means 1H2. That is given as 1.1 mega electron volt. Similarly, the binding energy per nucleon for helium nucleus is 7 mega electron volt. So this is the specific binding energy for deuterium. Similarly, the specific binding energy for alpha particle, that is helium nucleus, 2He4, which is equal to 7 mega electron volt. Now, they are asking to find what is the energy released. What is the energy released? Now they are telling that the two deuterons nuclei, two deuterons, 2 times of 1H2, two deuterons nuclei react to form a single helium nucleus. Single helium nucleus, that is 2He4. 2 times of deuteron is equal to 2 deuterium is equal to 1 single helium nucleus. So energy released means what? Binding energy of the reactant difference, the binding energy of the product. That is the energy released. But they have not given the binding energy. Instead of that, they have given the specific binding energy. You know the formula for the specific binding energy, isn't it? Specific binding energy is equal to binding energy divided by mass number. Specific binding energy is equal to binding energy divided by mass number. So this implies clearly binding energy is equal to specific binding energy into mass number. Specific binding energy into mass number. Correct, no? Now, can you calculate what is the binding energy of the reactant? Binding energy of the reactant means 2 times deuterium is there. So 2 times of specific binding energy of deuterium into mass number. 2 into. What is specific binding energy of deuterium? It is 1.1 mega electron volt into 2. That is 4.4 mega electron volt. 1.1 into 2 into 2. 2 into 2 will be 4. 4 into 1.1 will be 4.4 mega electron volt. After finding the binding energy of the reactant, you have to find the binding energy of the product. So what is the binding energy of the product? Here it is only one alpha particle. So specific binding energy into mass number of the alpha particle. What is specific binding energy of the alpha particle? That is 7 mega electron volt into mass number of the alpha particle, that is 4. So that is equal to 28 mega electron volt. So binding energy of the proton, product, is 28 mega electron volt, and binding energy of the reactant is 4.4 mega electron volt. So what is the energy released? Mass of the energy of the product, that is 28, minus binding energy of the reactant, that is 4.4, that is equal to 23.6 electron volt. So which is the right option? Option C is the right answer. So 23.6 electron volt is the energy released in the given nuclear reaction. So one thing you have to note down here, whenever they are asking you to find the energy released, means it must be the difference of the binding energy, not specific binding energy. So don't directly subtract this two. So energy released is always the difference between the two binding energy. Got it? So option C is the right answer. Yeah. Look at this problem. Just have an eye on the problem. What it is given? There is a nucleus with mass number 220, initially at rest. It emits alpha particle. What is the Q value of the reaction? 5.5 mega electron volt. That is energy released in the reaction. What they're asking you to calculate, they're asking you to calculate the kinetic energy of the alpha particle. You know that alpha particle is nothing but what? Helium nuclei, 2He4. Helium nuclei is the alpha particle. So there is one nuclei which is having a mass number 220 initially. We don't know what is Z. X mass number is given 220. This is going to emit an alpha particle. This is initially at rest. After emitting the alpha particle, there will be Z minus 2. Why? This 220 will become what? 216, because mass number has to decrease by 4. Plus which particle is released? Alpha particle is released, that is 2He4. So clearly they are expecting you to find what is the kinetic energy of this alpha particle. Kinetic energy of this alpha particle. And this reaction is releasing an energy of about 5.5 is the energy it is released in mega electron volt. But what is the formula? We have to find the kinetic energy. It is half mv square. If you want to find the kinetic energy, that is half mv squared, you must know what is the velocity of the alpha particle, that is helium nuclei. To find the alpha particle velocity, you have to make use of the conservation momentum. You have to make use of the conservation of what? The momentum. So what is the momentum formula? You know that. What is the momentum formula? You know that. momentum is denoted with the symbol P. That momentum is given by the formula square root of 2 times of mass into kinetic energy. What is EK represents? Kinetic energy. So here one alpha particle, the another one is going to be the reactant nuclei molecule. So you take the conservation of that momentum, you know the mass number conservation. Since the momentum is conserved, momentum of the first particle must be equal to the momentum of the alpha particle, second one, that is alpha particle. What is the momentum formula? Root of 2 times of mass. What is the mass of the daughter nuclei? You got it. After reducing to mass number into alpha particle, that is 4, remaining mass will be 216, right? So 216 into the kinetic energy of K1, which is equal to momentum of the alpha particle is 2 into mass of alpha particle, that is 4, into kinetic energy of that particle, that is K2. So on cross multiplication, on cancelling this root, it will be 2 into 216 into K1 is equal to 8 times of K2. So this you can cancel out. This is 4s are. Then you can cancel even this also. 4 1s are 454s are. So clearly this tells K2 plus or K2 is equal to 54 times of K1. K2 is equal to 54 times of K1. What is the total kinetic energy they have given? K1 plus K2, that is the Q value they have given. It is 5.5 mega electron volt, right? K1 plus K2 is 5.5 mega electron volt. So what is K1 from this? You can simplify this. You have to solve for K2. So K1 will be what? 5.5 minus K2. Substitute this K1 here. So what you will get? K2 will be 54 into K1. K1 is 5.5 minus K2. So on simplification of this, or if I want to simplify that, you have to tell me what is 54 into 5.5. What is 54 into 5.5? It is close to 297, I think. Yeah, 297 minus 54 K2. Shift 54 K2 this side. So it becomes 55 K2, which is equal to 297. So what is K2 from this? 297 divided by 55. So you will get approximately as 5.4 mega electron volt. So what is the kinetic energy of the second particle? Kinetic energy of the second particle, that is alpha particle, is 5.4 mega electron volt. So which will be the right option? 5.4 mega electron volt means you have to take the option B. So option B will be the right answer. Got it? Yeah. So let me take up the concept of radioactivity. It is the same chapter only, nuclei chapter only, but under the nuclei, this is the concept, a small concept about the concept of radioactivity. Yes, if you considered a heavy nuclei, having mass number more than 200, this is heavy nuclei. Now, if this heavy nuclei start disintegrating, then it start emitting certain invisible radiations. it start emitting invisible radiation. So this phenomenon is what we call as the radioactivity. So radioactivity means when every nuclei is start disintegrating into small nuclei, it will emit certain invisible radiation. That phenomenon we call it as a radioactivity. So whenever that radiations are emitted, those three radiations we have considered as alpha radiation, beta radiation, and gamma radiation. Alpha, beta, and gamma radiations. Suppose if you considered a heavy nuclei, let us say ZXA, if this is emitting alpha, please remember atomic number will decrease by 2 and mass number will decrease by 4. So whatever the resulting extra nuclei we are getting, that is what we considered as a helium nuclei, that is 2He4. So whenever the heavy nuclei emits alpha radiation, mass number will decrease by 4, atomic number will decrease by 2. Similarly, when heavy nuclei emits beta particle with negative beta decay, mass number will remain same, atomic number will increases by 1. So whatever the extra particle we are getting, that will be a electron nuclei, that is -1E0. Addition to this electron, actually one extra particle will come out according to some conservation of energy, which was explained by the scientist called by the name Pauli. According to that, this particle we considered as an anti-neutrino. To conserve the energy, we are getting that. So whenever this heavy nuclei emits beta plus, mass number will be the remain same, atomic number will decreases by 1, but here we are going to get +1 is 0. This +1 is 0, we call it as a positron. This is what we called as positron. Whenever the positron is emitted, there we are going to get just a neutrino. And please remember, this positron is just the antiparticle of electron. Antiparticle of electron means the characteristics will be remain same. Only the charge nature is going to be opposite to that particle. You know that electron is going to be having a negative nature. So positron will be having positive charge nature. But the characteristics will be the same. And please remember, this positron is not like a proton. So this is how the heavy nuclei is going to disintegrate into alpha, beta, and gamma radiations. Yeah. Coming to the next concept, that is the radioactive decay law. Radioactive decay law. What is this radioactive decay law or the radioactive disintegration tells? Suppose if you consider the rate of disintegration of an atom, dN by dt. What is dN by dt tells? Rate of disintegration of an atom. This rate of disintegration of an atom is directly proportional to the number of atoms remain in the sample. I mean to say that if that sample is having more number of atoms, you can disintegrate more. So you can disintegrate more if the sample is having more number of atoms. So dN by dt is directly proportional to the number of atoms. Sir, why we are writing this negative sign? If you start disintegrating, as the time changes, the number of atoms remaining in the sample will decrease or increase. The number of atoms remaining in the sample will decrease, right? So as the time increases, number of elements in the sample will decreases. So only we are going to write with that negative sign. So finally we are getting the equation of the atom that is the number of atoms remain in the sample after disintegration, that is given by the formula n is equal to n naught into e power minus lambda t. So what is the formula for the number of atoms remain in the sample? Number of atoms remain in the sample is equal to n is equal to n naught into e power minus lambda t, where lambda is a constant called the decay constant, t is called as the time, n naught is called as the initial number of atoms, and this n is considered as the number of atoms remain in the sample after this integration. So if you just calculate what is the rate of disintegration, so this actually dn by dt tells how many number of atoms is disintegrated in 1 second, because dt is the number of atoms disintegrated in a time of dt seconds. So if you want to find the number of atoms disintegrated in 1 second, then you have to take it as dn by dt. That dn by dt is considered as an activity A. So what is activity A? Rate of disintegration of an atom, that is number of atoms disintegrated in 1 second. So that is A is equal to dn by dt, which is nothing but lambda into n, where this lambda is a constant called the decay constant. So you have to remember this formula. Now, let me know what is the SI unit of the activity. What's the SI unit of the activity? So the SI unit of the activity is becquerel. Or you can also explain that in terms of disintegration per second. So 1 becquerel is nothing but 1 disintegration per second. So what is the SI unit of the radioactivity? SI unit of radioactivity is disintegration per second. So 1 becquerel is equal to 1 disintegration per second. So Curie and the Rutherford. So 1 Curie is equal to 3.7 into 10 power 10 disintegration per second. What is that? 1 Curie equals to? 1 Curie is equal to 3.7 into 10 power 10 disintegration per second. One Rutherford is equal to how many disintegration per second? 10 power 6 disintegration per second. So please remember this. We required this in the case of problems. 1 Curie equals to 3.7 into 10 power 10 disintegration per second. Next, you must know the concepts of half-life and mean life, students. What is half-life and the mean life? Suppose if I consider a sample having 100 nuclei, to make this exactly into half, that is 50 nuclei. So 100 nuclei has to come to 50 nuclei. So whatever the time is taken to come from 100 nuclei to 50 nuclei, that time is what we call as the half-life. What is half-life? Half-life is the time taken to disintegrate exactly half of the initial number of atoms. Initially, how many number of atoms will be there? To reduce to half of that, we require a certain time. That time we call it as an half-life. So that half-life actually is given by the formula 0.693 divided by lambda. Half-life is equal to 0.693. Okay. ನಾನು ಮೊಬೈಲ್ ಚಾರ್ಜ್ ಹಾಕ್ತೀನಿ ಅಲ್ಲ ನಾನು ಮೊಬೈಲ್ ಚಾರ್ಜ್ ಹಾಕ್ತೀನಿ ಹಾಕಿದ್ಬಿಡು ಇಲ್ಲಿ ಬಿಡು ನನ್ನ ಚಾರ್ಜ್ ಇಲ್ಲ ನಾನು ಹೇಳ್ತೀನಿ ಬಿಡು ಅನ್ನಂಗೆ ನೀ ಕಣ್ಣಿಗೆ Yeah. So whatever the time is taken to disintegrate exactly off of the initial number of atoms, that time is what we call as the half-life. That is given by the formula 0.693 by lambda. Suppose initial number of atoms is n. To reduce to half of that initial, let me take n naught. Half of that n naught by 2, one half-life is taken place. If I take one more half-life, n naught by 4, it will be 2 half-life. If I take one more half-life, it will be 3 half-life. So in general, if there are n half-lives, has taken place, after n number of half-lives, the number of atoms will become 1 by 2 power n into n naught. Because this can be taken as 2 squared, this can be taken as 2 cube. After 2 half-lives, 2 squared. After 3 half-lives, 2 cube. So after n number of half-lives, what will be the number of atoms remaining in the sample? It will be 1 by 2 power n into n naught. What is n represents there? N represents the number of half-lives. Number of half-lives. So if you consider n number of half-lives, after n number of half-lives, the number of atoms remaining in the sample is 1 by 2 power n into n naught, where n represents the number of half-lives. Then, how to calculate the mean life or the average life? You know how to take the mean life? What is mean life or an average life? It is the total life of all the atoms to the total number of atoms. This ratio is called as the mean life. You know how to take the mean life. Mean life is considered as the total life of all the atoms total of life of all atoms to the total number of atoms. This ratio is what we call as the mean life. And please remember, mean life is the reciprocal of the wavelength, decay constant. So you can prove that the half-life is the reciprocal of the decay constant, that is 1 by lambda. So what's the formula for half-life? T off is equal to 0.693 divided by lambda. So T off equals to, this can be taken as 1 by lambda into 0.693. So you can take that half-life as mean life, 1 by lambda as mean life, tau. So tau into 0.693. This is the relationship between the half-life and the mean life. So half-life is equal to mean life into 0.693. So these are the three important formulas, students, you have to remember in this radioactivity, where the problems will be very simple in this case. Yeah. Consider this problem. There is a radioactive substance that decays to 1/16th of its initial activity. 1/16th. Look at this. 1/16. 1/16 can be considered as 1/2 power 4. 2 to the 4, 4 to the 8, 8 to the 16. 2 power 4 will be 16, right? Yeah. As I explained, what is this 4 represents? What is this 4 represents? This 4 represents the number of off-lives, isn't it? What is that 4 represents? Number of off-lives. Now, what they have given, initially activity is how much? N0. To come to 1/16th, what is the number of times that it has taken? 40 days. Now, what they are expressing, the off-life. You know that the total time divided by the off-life always represents the number of off-lives. How to calculate the number of off-lives? Total life divided by off-life. So what is the total time? 40 days. What is the off-life? You have to calculate. What is the number of off-lives we have got? 4. So what is T of 40/4? What is 40/4? 40/4 will be 10. So what is the off-life, students? It is 10 days. So what is the off-life? Off-life is the 10 days. So which is the right option? Option C. Yeah. There is a sample of radioactive element that has a mass of 10 gram initially. So what is initial mass? I can take N0 or M0, whatever it is, 10 gram. What is the approximate of this element in the sample after 2 mean lives? 2 mean lives. So what is the time? 2 mean lives. After 2 mean life, what will be the mass? Yeah. Yeah. How to get this? You know that the number of atoms remaining in the sample is given by the formula n is equal to n0 into e power minus lambda t. So n will be equal to m. N0 is m0. E power minus lambda, time is nothing but 2 times of mean life. And you know that mean life is nothing but the reciprocal of decay constant. So this lambda and lambda will get cancelled out. So m is equal to m0 into e power minus 2. Or m will be equal to m0 divided by e power 2. What is m0? 10 gram. You know that E is the Napier's constant, that is 2.173 whole square. So if you go with the simplification of this, 10 divided by 2.713. First you have to go with 2.713 square. You will get approximately 7 point something, that is 7.36, I think. Yeah, 7.36. Then if you calculate 10 divided by 7.36, you are going to get 1.358 or 1.35 grams. So after two mean lives, the number of atoms or mass remaining in the sample is 1.35 gram. That is option D. Yeah, come to this. Half-life of this element is given as 100 microsecond. Half-life, T of 100 microsecond. Now they are expecting you to find what is the time taken to reduce to 1/16th of the sample. To reduce to 1/16th of the initial value. Yeah, 1/16 can be taken as 1/2 power 4. Yeah. What is this 4 indicates, students? The number of half-lives, isn't it? That 4 represents the number of half-lives, isn't it? Yeah. For one half-life, what is the time it is going to consider? 100 microsecond. For one half-life, the time taken is 100 microsecond. This implies for 4 half-lives, so the time taken will be 400 microsecond. So for one half-life, the time taken is 100 microsecond. For 4 half-lives, the time taken is 400 microsecond. So which is the right option? Option A. 400 microsecond. 400 microsecond. Yeah. Look at this. The mean life of the radioactive substance which is emitting alpha and beta emissions are 1620 years and 405 years respectively. Mean life for alpha 1620 years. Mean life for beta 405 years. After how much time it will reduce to 1/4? Whatever the initial is there, it is going to reach to 1/4. Initial of 1/4. What is the time? See here. Here the two concentration is taking place. One is for alpha, the another one is for beta. So the total decay constant is equal to decay constant of alpha plus decay constant of beta. That is 1 divided by 1620 plus 1 divided by 405. After simplification, you are getting this much. That is 1 divided by 324 per year. So this is lambda. That is the disintegration constant after combining alpha and beta nuclei. Now they are asking you to get 1/4 of the initial. What is the activity? 1/4 of the initial activity. 1/4 of A0. So you know that activity is given by the formula A0 into e power minus lambda t. A is 1/4 times of A0. 1/4 of that. After remaining is A naught by 4. So this A can be taken as A naught by 4. So it will become 1 by 4. E power minus lambda is 1 by 324 into T. Or on taking reciprocal, it becomes E power T by 324. So you know that taking log on both the side, log 4 is equal to log E power T by 324. So log 4 value is how much? Log 4 can be taken as log 2 square. So it will be 2 log 2. This is T divided by 324. So this log E base E value will become 1. You know that 2 log 2 value will be how much? 2 log 2, and this is base E. So this is 0.693 equals to T divided by 324. So you can do the cross multiplication this. If you cross multiply, what you are going to get? It is approximately 449. So you're going to get the time as 449 years. So which will be the right option? Yeah, option C. 449 years. Yeah. Come to this problem. At any instant, the ratio of the amount of radioactive substance will be 2:1. Half-life will be 12 and 6 hours. If I consider there is a sample A and sample B, initially if this is having 2, this will be having 1. What is the half-life for this? 12 hours. What is the half-life for B? 16 hours. Now they are telling after 2 days. After 2 days means here totally 4 half-lives has to take place. Why 4 half-lives? Because 12 hours, 1 half-life. 2 days means 48 hours. 2 days anta andre, it is 48 hours, no. So if the half-life is 12 hours, so how many half-lives you can expect in 2 days? 4 half-lives. So if the second nuclei is 1 initially and half-life is 16 hours, so how many half-lives will be possible in 2 days? 3 half-lives. So 3 half-lives will be possible. 3 half-lives will be possible in 2 days for the sample B. So for after 4 half-lives, after 1 half-life it will come to 1. After second half-life 1 by 2, that is 0.25, or you can consider it as 1 by 2. Next half-life will be 1 by 4. 1, 2, 3. Still one or more half-life. Third half-life 1 by 16. So after 4 half-lives, the sample A is having only 1 by 16. Come to B, only 3 half-lives. So after 1 half-life, it will be 1 by 2. After second half-life, 1 by 4. After third half-life, it will be 1 by, half of that 1 by 8. Here also half of 1 by 4 is 1 by 8. Sorry, 1 by 8. So sample A is also having 1 by 8. Sample B is also having 1 by 8. If I take the ratio, it will be 1:1. If I take the ratio, it will be 1:1. Yeah. From a newly formed radioactive sample, half-life is 2 hours. So what is half-life? 2 hours. The intensity of the radiation is 64 times the permissible safe level. So up to 64 times, nothing will happen. It is permissible for the safe level. Then what is the minimum time after which work can be done safely from this source? 64 times. So 64 times means 1 by 64 times means 2 power how much? 2 twos are 4, 4 twos are 8, 8 twos are 16, 16 twos are 32, 32 twos are 64. So 1 by 2 power 6 is 1 by 64. That means how many off lives it has to undergo? It has to undergo 6 off lives. It has to undergo 6 off lives to work with a safe level. So for one off life, what is the time taken? 2 hours. For 6 off lives, the total time will be 2 into 6, right? That should be 12 hours. So option B will be the right answer. Option B will be the right answer. Yeah. Nucleus of mass number A originally at rest. ZXA. This is initially at rest. It emits alpha particle. Alpha particle means 2He4. The speed of this will be V. The daughter nucleus will be A minus 4, Y, Z minus 2, right? Mass number will decrease by 2. Mass number will decrease by 4. We don't know what is the speed of this daughter nuclei. Let it be V1. They're expecting you to find V1 only. You know the conservation of momentum. So momentum of the daughter nuclei must be equal to the momentum of the helium nuclei. What is momentum? Mass into velocity. Mass is A minus 4 into V1 equals to, what is the mass here? 4 into V. 4 into V. What is V1 from this equation? V1 is the velocity of the daughter nuclei. That is 4 times of V divided by A minus 4. So V1 will be equal to 4 times of V divided by A minus 4. So you can go with option C. 4V divided by A minus 4. Option C. Come to this problem. The counting rate observed from the radioactive source at T is equal to 0 is 1600 counts per second. So initially it is 1600 counts per second. After 8 seconds, it was 100. After 8 seconds, T equals 8 seconds, the count becomes 100. Clear? Observe carefully here. 1600. For one half-life, it will become 800. For second half-life, it will become 400. For next half-life, it will become 200. For next half-life, it will become 100. So 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. After 4 half-life, it is coming to 100. So in 8 seconds, how many half-lives is taking place? 4 half-lives. So in 8 seconds, 4 half-lives are taking place means what should be the half-life? Half-life will be 2 seconds, right? Half-life is 2 seconds. So in 8 seconds, how many half-lives are possible? 4 half-lives. So for 4 half-lives, in 8 seconds means half-life must be 2 seconds. Half-life must be 2 seconds. But what they are expecting? They are expecting the count for 6 seconds. They are expecting the counts for 6 seconds. So for 2 seconds, the count will become off. So 6 seconds means 3 off lives. Six seconds means 3 off lives. 3 off lives means starts from initially 1600, 1 off life, second off life. This is the third off life. So in the third off life, it is coming to be 200. So option C. Option C is the right answer. Yeah. Kinetic energy of the neutron beam is given. That is 0.0837 electron volt. Half-life of this neutron is 693 seconds. Mass of the neutron is 1.675 into 10 power minus 27 kg. What is the fraction of decay in traveling a distance of 40 meters? So starting from this, it has traveled a distance of 40 meters. After traveling 40 meters, what will be the fraction of the decay? What fraction it is going to be decayed in traveling a distance of 40 meters? First, you have to calculate what is the time taken by the neutron to travel this distance of 40 meters with a kinetic energy of 0.0837. Yeah, I can show the calculations part to your students. The kinetic energy is nothing but half mv square. So you can calculate what is V. That is 2 times of kinetic energy by mass under the root. So 2 times of kinetic energy by mass. So they have given the kinetic energy and also they have given the mass. If you calculate that, it is found to be 4 into 10 power 3 meter per second. Energy is given by 0.0837 electron volt. You know how to convert that electron volt into joule by multiplying with 1.6 into 10 power minus 19. So you are going to be 4 into 10 power 3 meter per second. So with this velocity, what is the time taken to travel a distance of 40 meter? It is 10 power minus 2 second. 10 power minus 2 second. Then what is activity dN by dt? dN by dt is nothing but lambda into n. Or you can take dN by n is lambda into dt. This dN by dN is called the decay of the fraction of the sample. So how much of fraction of the neutron has decayed means delta n by n or dN by n. That is nothing but lambda into delta t. You know that lambda is nothing but 0.693 by off life. So 0.693 by off life I have taken as 693. Into the time you got it as 10 power minus 2 second. So totally it will be 10 power minus 5. So what is the fraction it has reached? 10 power minus 5. So option C is the right answer. Got it? Just you can have a look on this calculation part, student. Yeah, let me see the next problem. The fraction of the atoms of the radioactive element that decays in 6 days. So time taken is 6 days. That decay 7 by 8. So what is remaining? Remaining is 1 by 8, no? Initially, if you have 1, decayed means disintegrated. Decayed is 7 by 8. So what is remaining? Remaining is difference. 1 minus 7 by 8. That is 1 by 8. So the number of atoms remaining in the sample is 1 by 8. And now they are asking you to find the fraction that decays. That fraction that decays in 10 days. The fraction that decays in 10 days. So when the initial comes to be 1 by 8, 1 by 8 means 1 by 2 cube. 1 by 2 cube means 3 off-lives. How many off-life it has taken place? 3 off-lives has taken place in 6 days. So what is the off-life? 2 days. Off-life here is 2 days. Now they are expecting the fraction for 10 days. Look at the fraction for 10 days. So for 10 days, you can see the concept here. N equals to n naught into e power minus lambda t. That on simplification, you can take it as number of atoms is equal to 1 by 2 power n into n naught, right? What is this n represents? Total time divided by off-life. So that I am substituting here. So what is n naught? N into 2 power n. So n is what? T by T of. So clearly that tells T is directly proportional to log base E n naught by n. Take the 2 times because one is 6 days and the another one is 10. So take the ratio 6 by 10. For 6, if the ratio is 8 by 1. For 10, how much? We don't know. Let it be n naught by n. So 2 6s are 2 3s are 2 5s are. On cross multiplication, you will get log base E 32 value will be n by n naught. Log base E can be cancelled out. So n naught by n, you will get it as 32. So this is remaining. This is remaining in the sample. But they are asking you to find the decay. Decay means 1 minus remaining. That is 1 minus 1 by 32. So what will be the LCM? 32. So 32 minus 1 will be 31. So what will be the number of atoms that decays? The number of atoms that decays will be 31 by 2. So option C is the right answer. Option C is the right answer. Here also you can have the calculation look up. I have not written the solution. Just you can have the solution here. On simplification, you can find the decayed sample will be equal to 31 divided by 32. I hope you got the concepts of radioactivity concepts, isn't it? Yeah. So I can stop at this stage, students. In the next class, I can take up the next chapter, that is semiconductor electronic devices. Actually, after semiconductor electronic devices, I left out with one small chapter that is in the part 1, I think. That is electromagnetic waves. So in the next coming classes, I can take up these 2 chapters. That is semiconductor electronic devices and electromagnetic waves. So I will stop at this stage, which completes the nuclei chapter, students. So in the next class, I'll start up the new chapter, that is semiconductors. Thank you.